Thank you very much.
Hi, I'm Giovanni, and I'm going to talk about learning affordances. This is work from the Técnico project done with a bunch of people from IST and KTH. And I'm going to talk about a computational implementation of object affordances for humanoid robots, and mostly talk about an extension with tool usage, where tool usage emerges from robot exploration. And then briefly talk about two other extensions with language grounding and action recognition. And the basic motivation is that we learn affordances by exploring the environment. And this is framed within the embodied cognition framework, which means that this exploration is highly dependent on the agent's body, on the sensory motor capabilities. And the way kids explore the world and learn affordances is basically by interacting with it, playing with it, with their body, precisely, so sensory motor capabilities. This is very personal. And another possibility of learning affordances is that we are able to predict the consequences of physical actions, and in some cases tackle uncertainty problems and react to unexpected events. So the classical Gibsonian affordances are defined as action possibilities present in the environment related to the agent's sensory motor capabilities. And I cannot stress enough the fact that affordances are personal. That means that, for example, to operate a door handle, the experience is very different if you are an adult, a kid, a dog, or a robot. So these are not characteristics of just the object per se, but they are linked to the sensory motor capabilities. And a few years ago, Montesano proposed a possible probabilistic implementation to capture these object affordances. And basically, he encodes affordances as relationships between physical actions, objects in the world, and the resulting effects of the actions. It's a model based on Bayesian networks, which is nice because it's quite flexible. It allows us to do inferences and estimation on any set of variables given any other set of variables after we have learned the model. So we can do a number of things with this model. We can predict an effect given the object of interest and a possible action, or we can plan the action given object and effect, or just the object, or we can even estimate the properties of an object by marginalizing over the effect and action properties. It turns out, however, that many daily activities are quite complex in the sense that they involve multiple objects for an agent. Typically, in many activities, we have an agent holding an object and then acting upon another object. What I'm going to talk about is an extension of the basic Montesano affordance implementation, tackling this multi-object scenario. And quite simply, this means we have expanded the object part by considering held object and acted object separately. Note that we do not impose restrictions as to which objects are tools or held and which ones are acted. This can be learned by exploration by a robotic agent. And so this model is slightly more complex than the previous one. It allows us to do more precise inferences, such as which held object, which tool is ideal for for a manipulation action or some properties of an object, whether is it held or acted upon. And the way we measure features in our probabilistic model is basically by computational geometry. We take the silhouette of a normalized image from the robot, and we compute some shape descriptors from it. This means we are not doing object categorization or object classification. We do not encode any labels, and we do not introduce any categories of cups or balls or toys. We just compute low-level visual descriptors, and this has a neuroscientific motivation of sorts, because there is evidence that some perceptual features of objects are directly linked to the motor areas that get activated without reasoning about categories or similarities to previously seen objects. So, in the top video, you can see the iCub robot performing some exploration cycle, which is composed of seeing a held object, seeing an acted object, performing an action, and measuring the effects. In this case, the actions are predefined, and the effects are simply physical displacement of the held object. For efficiency reasons and for time, we train our model in simulation. That's in the bottom video. We reproduced the exploration cycles and ran about 2,000 experiments, acquiring and recording data, and then building the probabilistic model of affordances from it. However, I will show you that the data acquired in simulation can be generalized in some cases to the real robot scenario. So basically, with the data acquired in simulation, we tested a few different Bayesian networks. I won't go into details, but the baseline network is a fully connected, manually specified network, which means we define that all object properties, both held and acted, and the action node are connected to the observed effect. And so you get lots of links in the top picture. The other two structures are learned, and the one in the middle is structural learning, K2 algorithm, so it's completely learned by exploration, both the connections, the structure of the network, and the parameters, the weights. And the bottom network is a principal component analysis or dimensionality reduction network from the exploration data. So each of these networks have some pros and cons, and the learned ones certainly are more efficient in terms of times and complexity in number of nodes and parameters, faster to train, and require less data compared to the baseline to learn a meaningful affordance network. However, in some cases, we can suffer from overfitting. Okay, thank you. So, as I was saying, we can generalize from the learned from the simulation data to a real robot scenario, predicting the physical effect. That's comparison between those two histograms below the 10% of the worst case scenario. So very quickly, another extension of the basic affordance model has to do with language grounding, which means we not only record and measure the physical affordances and visual affordances of the robot, but we relate it to language as well, to an external narrator. It's a simple bag-of-words model, no language, just speech recognition, but it's useful to detect impossible tasks or solve ambiguities, such as roll the blue object when we have two objects visually. And the last extension to the model has to do with action recognition. So it's nice is for the action part of the affordance model, we can relate it to a human partner for interactions. That means the action is not longer predetermined, but it can be measured with some mirroring and then mapped from the partner to the robot. So the key point is that we can learn object affordances by exploration. It's an open-ended learning, quite general model that can be extended. I show mainly the tool usage, emergence, and the other extensions. Thank you.
We have time for questions. Yes?
The question you had, you showed this kind of extended Bayesian model with 4 nodes instead of 3 nodes.
Right.
But some objects can presumably be of both types. They can both be
Yes.
manipulated and be the tool. Yeah. So
Right. So we don't specify that beforehand, but this can be learned by exploration. For example, we have some sticks, elongated object, and some toys or balls, and the robot tries all possible combinations. So even to move the stick by using the ball as a tool. So this doesn't work, and the corresponding parameters will be learned.
To allow an object to be in both the T and the O, it can be in both sets. Yeah.
Yes.
These sets can overlap.
Yeah. But basically, the Bayesian network is a big table, and we can fill up the combinations. In this case, we will have different values, both non-zero, or in the case of stick and ball, we observed that it was a tool.
So thinking beyond it, usually we think about tools that you use to make other tools. Using a stick or something, you make a tool. I'm not sure if it's observed in
Oh, you mean like assembling?
Yeah, assembly. It's very important in human technology. We make tools that let us build other tools.
Yes.
But that's
That's
going beyond.
That's an interesting possibility.
Another question, perhaps? Yes, please.
Could you go back to the slide where you showed like a bunch of different networks? That, that one. What? Since we have a little time, could you go into a little more? You mentioned that you use principal component analysis, but you also said they were hand built. So
the first network is a completely specified, hand built. So we connected all the object properties, all the action properties, all the tool properties to the observed effects and learn the parameters. In the structured learning A2, everything was learned from exploration, both the structure and the parameters. PCA lies a bit in the middle, so we measured empirically that for our 2,000 experiments, 2 principal components were enough to cover enough values, so we specified 2 components, and then we learned the parameters. In our experience, PCA is quite good because it's much less complex to train table compared to the baseline. Still, it shows reasonable generalization capabilities to novel objects, for example, with similar affordances. We trained about 7 objects in simulation.
do you have a paper about that slide?
Yes, I submitted it to ICDL.
Okay.
Thank you very much.